Motion in space, velocity and acceleration. Velocity and acceleration are both taught in Calculus 1. The lesson here is very similar. So if we have a point moving along a path, we know that we can get the average velocity by finding the slope of the secant line. Now in this case, that would just be the vector going through points P and Q. And then to get the velocity at a particular point like P, we just take the limit as h goes to 0 of the slope of this tangent vector. Now this is what we call the velocity vector, and it should come as no surprise that it is the derivative of the position vector. If you take the magnitude of this velocity vector, this is the magnitude of the derivative of the position, which we know is ds dt, which is the rate of change of the distance with respect to time. So in short, when you take the magnitude of the velocity vector, you are getting the speed of the object. Remember, velocity is a vector, which has both a magnitude and direction. But when you take the magnitude of the velocity vector, you are just looking at the speed. And acceleration is the rate of change of the velocity, and so the acceleration vector function is just the derivative of the velocity function, or the second derivative of the position function. So as an example, suppose we know the position vector of an object moving in a plane is given by the function r that you see here, and this is in 2 dimensions, right, because we're in a plane. Find its velocity, speed, and acceleration when t equals 1. Okay, so first of all, let's go ahead and write down the position function, r of t. I'm going to write it in this format, t cubed, comma, t squared. And then the velocity function is just r prime. And if we take the derivatives here, we get 3t squared and 2t. So this is the velocity vector. Now the velocity at t equals 1 is simply plugging 1 into here, and that's going to give us the vector 3, 2. Now the speed is the magnitude of this vector, and this will be the square root of 3 squared plus 2 squared, which is the square root of 13. Now the acceleration function, a of t, is just the second derivative of r, or if you like, we can call it the first derivative of velocity. So basically, we're just going to take the derivative of this, which gives us 6t and 2. And the acceleration when t equals 1 is going to be a of 1, which of course is just 6, 2. Now we have the graph of the position function here. We have the velocity at t equals 1 here, and we have the acceleration here. So you'll notice that the velocity vector is tangent to the curve, but the acceleration vector is not. Next, let's find the velocity, acceleration, and speed of a particle with position vector r given here. So once again, the velocity vector is simply the derivative of each component, which will be 2t e to the t, and then the derivative of t times e to the t is t e to the t plus 1 times e to the t. So it is e to the t times t plus 1. So this is our velocity vector. The acceleration vector is the derivative of that, which is going to be 2 e to the t, and then the derivative of e to the t times t plus 1 will be e to the t times t plus 1 plus e to the t times 1. And this is e to the t times t plus 1, which is e to the t times t plus 2. And then the speed is just the magnitude of the velocity vector, which is the square root of 2t quantity squared plus e to the t, quantity squared, plus e to the t times t plus 1, quantity squared. And if we simplify this, we get the square root of 4t squared plus e to the 2t plus e to the 2t times t plus 1 squared. And if we multiply this out, we're going to have 4t squared plus e to the t, 2t, plus t squared e to the 2t, plus 2t e to the 2t, plus e to the 2t. And then combining like terms here, we end up with t squared e to the 2t plus 2t e to the 2t plus 2e to the 2t plus 4t squared. And this is the speed at any time t, and of course square root of the whole thing. So velocity vector is here, acceleration vector is here, and the speed is this scalar quantity. In the next example, a moving particle starts with an initial position r of 0 equals the vector 1, 0, 0, and initial velocity I minus j plus k. Its acceleration is the following vector function. We want to find its velocity and position at time t. So let's recall from Calculus 1 that if you know the acceleration function, you can take the antiderivative of that function to find the velocity function. Now, if you're doing this on a particular interval of time, let's say from t0 to t, then you get the following formula. And the v of t0 here is simply the initial velocity. And then once you have the velocity function, you can find the position function by taking the antiderivative of the velocity function and adding the initial position. All right, so let's go ahead and do this problem here. So first we'll find the velocity function, v of t, and we'll do this by doing v of t0, okay? And t0 is 0 because they tell us that time equals 0 here in these initial conditions that they give us. Plus, then we're going to integrate from 0 to t the acceleration as a function of u, okay? And so here we have the acceleration as a function of t. So I'm just going to replace the t with a u. So we get 4u, 6u, and then 1. And this will be du. So to do this, we simply need to integrate each of those components. So we have v of 0, which is this number here, which is simply 1, negative 1, 1, plus the antiderivative of each of these. So the antiderivative of 4u is going to be 2u squared, but then we have to evaluate it from 0 to t. Then we have the next component is 6u squared divided by 2, which is 3u squared, again going from 0 to t. And finally, the antiderivative of 1 is u, and that also goes from 0 to t. Now, the notation here is probably not commonly used, but I find this to be actually pretty practical. So I'm just going to apply the fundamental theorem of calculus on each one of these, which means plugging in t for u. And of course, when you plug in 0, you get 0 for all of these. And so this simply becomes 2t squared, 3t squared, and t. And so now altogether, we can write this as the vector function 2t squared plus 1, 3t squared minus 1, and t plus 1. And this is our velocity function at time t. Now to find the position function, r of t, we are simply going to take r of t naught, which is 0, plus the integral from 0 to t of our velocity function as a function of u. So that's basically this function right here, but I'm going to put a u in there. And so this becomes 2u squared plus 1, 3u squared minus 1, and u plus 1, du. Now we take the antiderivative, and let's remember that r of 0 was given to us. It is the point 1, 0, 0. Plus, and now we're just simply taking the antiderivative of each of these, which will be 2u cubed over 3 plus u from 0 to t. And then 3u cubed over 3, which is u cubed minus u from 0 to t. And finally, u squared over 2 plus u from 0 to t. Now, once again, plugging in t and plugging in 0 and applying the fundamental theorem of calculus here, we get 2/3 t cubed plus t to the third minus t, and t squared over 2 plus t. And adding these vectors together, we have 2/3 t cubed plus t plus 1, t cubed minus t, and t squared over 2 plus t, right? Because these two are 0, so it doesn't change these at all when you add them together. And this is our acceleration vector function. Next, let's consider an object with mass m that moves in a circular path, so it's moving around like this, with a constant angular speed omega. And it has a position vector equal to a cosine omega t times I plus a sine omega t times j. We want to find the force acting on this object and show that it is directed towards the origin. So let's remember that force is equal to mass times acceleration. And in this case, it's going to be mass times the acceleration vector function. So we need to find a of t. We know that the position function r of t is equal to a cosine omega t and a sine omega t. So the velocity function will be the first derivative of this. The derivative of cosine is negative sine, so we're going to have negative a sine omega t times the derivative of omega t, which is omega. And the derivative of sine is cosine, so we will have a cosine of omega t and then times the derivative of omega t, which is omega once again. So don't forget the chain rule here. And now for the acceleration function, it's just the second derivative. So we have negative a omega, these are constants, and then the derivative of sine of omega t is cosine omega t times another omega. So we have negative a omega squared cosine of omega t. And then for the second coordinate, derivative of of cosine is negative sine. So we get negative a omega times sine of omega t times another omega. So we get omega squared once again. And I want you to notice here that you have an omega squared and an omega squared and a negative and a negative. And I'm going to factor those out. And so this a of t can be rewritten as negative omega squared multiplied by a cosine omega t, a sine omega t. And pay attention to this because this is the original function r of t. And so what we have here is the acceleration function is negative omega squared times r of t. So our force vector is mass times acceleration. So it's simply mass, which is m, multiplied by this. So that is negative m omega squared multiplied by r of t. Now, r of t is the position vector, right? So if you have your point on the curve here, your position vector is this vector right here. What we can see is that the force vector is pointing in the opposite direction of that position vector. So we can see that our force vector is pointing inward toward the origin. Next, we have projectile motion. Suppose a projectile is fired with an angle of elevation alpha and an initial velocity v0. Assuming that air resistance is negligible and the only external force is due to gravity, find the position function r of t of the projectile. What value of alpha maximizes the range? Okay, so a projectile is fired at some angle alpha into the air. As you shoot it up, it's going to take a parabolic path like this, and eventually it's going to come down and touch the ground. So we want to find the vector function for the position of this path, and then also what value of alpha will maximize the distance traveled here. Let's think about what's happening as this object is fired into the air. So depending on the initial velocity the object is fired here, there is a horizontal component to that velocity and there is a vertical component to that velocity. So what I can do is represent those components here by making a triangle. And again, this will be the horizontal component and this will be the vertical component. So let's call this x. We know that x, which is the distance traveled here, is going to be the horizontal velocity multiplied by t. So let me call this Vx multiplied by t. And the y component is going to be Vy multiplied by t. So we have to find out, given an initial velocity v0, what is the initial velocity in the horizontal direction and what is the initial velocity in the vertical direction. So let's just increase the size of that triangle right there. We know that if this is a right triangle with angle alpha and this is v0, then we know that the vertical one here is v0 times the sine of alpha and the horizontal one is v0 times the cosine of alpha. And so we can call this v0 cosine of alpha multiplied by t, and this one v0 sine of alpha multiplied by t. But this only accounts for the position due to the initial velocity. The y component also has gravity working against it. So even though we fired this velocity upward, gravity is pulling down on that. So we need to find out how much does gravity work against this object. So basically, we know that the acceleration due to gravity is called g, and we'll put a negative in front of it to indicate that it's working in the opposite direction. Well, if that's true, then the velocity due to gravity is going to be negative g times t. And the position due to gravity, so we'll call that r, is going to be the antiderivative of this, which is negative 1/2 gt squared. So the position is affected by gravity by a factor of negative 1/2 gt squared. This is working against the position here. So the overall position in terms of y is going to be v0 sine of alpha times t minus 1/2 times gt squared. So the position vector r of t is going to have an x coordinate v0 cosine of alpha multiplied by t, and a y coordinate v0 sine of alpha multiplied by t minus 1/2 gt squared. Now, how do we find the horizontal distance traveled? Well, what we need to do is first figure out, when does it hit the ground? Well, it hits the ground when y is equal to 0, right? So as it moves along this path, we have an x coordinate and a y coordinate. When that y coordinate is 0 is when it hits the ground. So I'm going to set my y coordinate here equal to 0. So v0 sine of alpha times t minus 1/2 gt squared is equal to 0. I can factor out a t, and I get t times v0 sine of alpha minus 1/2 gt equals 0. Now, of course, this is going to happen when t equals 0, which is the beginning, but it's also going to happen when I set this equal to 0. And so if I have negative 1/2 gt equals v naught sine of alpha, we get gt is equal to, see, this should be negative here, is equal to 2 v naught sine of alpha, and t is going to be 2 v naught sine of alpha divided by g. So the total distance traveled at that particular time is going to be the x-coordinate of the position vector evaluated at this time. So the total distance traveled d is going to be v naught cosine of alpha multiplied by 2 v naught sine of alpha divided by g. Or if you simplify this, we have v naught squared, and then 2 sine of alpha cosine of alpha is the sine of 2 alpha divided by g. So this is the distance that it will travel. Now, when will that distance be maximized? This distance will be maximized when the value of sine is maximized, because notice that v naught is a constant and gravity is a constant. So sine is maximized here when theta equals pi over 4, because we know sine has a maximum value of 1, and that happens when this angle is pi over 2, and so alpha has to be pi over 4. So alpha equals pi over 4 will produce a distance of v naught squared divided by g. So basically 45 degrees. If you angle the path of this projectile to be fired at 45 degrees from the horizontal, this is going to produce a maximum distance traveled of v naught squared divided by g. In the last example, a projectile is fired with an initial speed of 150 meters per second and an angle of elevation of 30 degrees from a position 10 meters above ground level. Where does a projectile hit the ground and with what speed? First, let's recognize that x is equal to v naught cosine of alpha times t, and y is equal to v naught sine of alpha times t minus 1/2 gt squared. Now, that's not the entire position function in this case, because it's being fired at a position 10 meters above ground. So I have to add 10 here because it starts 10 meters above what you would call y equals 0. Also, g in this case is 9.8 meters per second squared, because we're given units this time. So we need to plug in the correct units for gravity. So we have y is equal to v naught, which is 150, sine of alpha, which is the sine of 30 degrees, all this multiplied by t, minus 1/2 times 9.8 times t squared plus 10. This is negative 4.9 t squared. Sine of 30 is 1/2 times 150 is 75, so plus 75 times t plus 10. Now the x distance traveled is going to be 150 cosine of 30 degrees times t, and that will be 150 times radical 3 over 2, or 75 radical 3 times t. So these are the parametric equations that describe your position of your particle. Now the second question is, where does the projectile hit the ground? First, we need to ask, when does it hit the ground? It hits the ground when y equals 0. So we're going to take negative 4.9 t squared plus 75t plus 10, set that equal to 0. And to solve this, we'll use the quadratic formula. So negative 75 plus or minus the square root of 75 squared minus 4 times negative 4.9 times 10, all divided by 2 times negative 4.9. This will produce two values of t. One value is going to be negative and one value is going to be positive, and the positive value is 15.44. So this object is going to hit the ground 15.44 seconds after it's been fired. So now where does a projectile hit the ground? Well, let's keep in mind what's happening here. So you have a projectile which started 10 meters above the ground, was fired at a particular angle, and now is coming down and hitting the ground. And it hits the ground here at t equals 15.44 seconds. So to find the distance traveled, we need to find the x value at this particular time. So the distance traveled is going to be 75 radical 3 multiplied by 15.44 seconds. And if we do the math on that, we get 2,006 meters. So that is the total distance traveled. Now we want to know with what velocity does it hit the ground. So for this, we need the velocity function. So let's find v of t. And just for notation's sake, first of all, let me represent the position function r of t. This is 75 radical 3 times t, and then negative 4.9 t squared plus 75t plus 10. So for the velocity function, v of t is going to be the derivative here, which is 75 radical 3. Then we're going to have negative 9.8 times t plus 75. Now, to find the speed when it hits the ground, we need to plug in the time where it hits the ground, which is 15.44 seconds. And then we also need to take the magnitude. So the speed is going to be the magnitude of the velocity at 15.44 seconds. And so that will be the square root of 75 radical 3 squared plus negative 9.8 times 15.44 plus 75 quantity squared. And if we do the math on that, we get 151, and this will be meters per second. And that concludes this video lesson.